Hey, I'm Tejas. Today we're going to be talking about concurrency in Postgres. So, as I said, my name is Tejas. I'm Tejas Manohar on pretty much all social media, GitHub, Twitter, etc. I'm an engineer over at Segment, which is a data infrastructure company that makes it really easy to get data into tools that let you analyze it from your app or your Salesforce account or many other services. So this talk is going to be about concurrency in Postgres. If you treat your database right now as like a black box and don't really know about how it handles concurrency, or you haven't written applications that handle concurrency before, then in this talk, first off, you'll learn about how the world, how your applications handle concurrency, and then about how Postgres implements concurrency control. We'll get into the implementation details a bit about what it stores, etc. And then lastly, we'll talk about how you should really think about concurrency control when you're dealing with Postgres. As a Postgres user, that's the most important thing. So first off, the big question that we ask when we think about different concurrency control mechanisms, performance, guarantees of databases, etc., is what do databases value? And to answer that, we really need to think about how we evaluate databases. So, of course, there's one line of thought. You need to evaluate database based on the cost. Is it a free license like Postgres? Is it Oracle? Is it MS SQL, etc.? Then there's also scope of features, like does your database support this feature on indexes or something else? But then there's a couple other points which are the most important in my opinion when you're choosing between technologies, which are performance and guarantees. And those pretty much go hand in hand, and that's what we're going to focus on whenever we talk about any of the mechanisms in this talk that Postgres uses. So what do databases guarantee? So when we talk about guarantees in databases, this is room for a lot of buzzwords. There's plenty of terms used to describe different databases and their guarantees. Some really give you a good idea, and some don't. For example, some people say databases are transactional. Some say that they're ACID compliant. Some say that they're base, the opposite of this. Some distributed stores are graded on something called the CAP theorem. In this talk, we'll start reducing the ambiguity around the ones that actually apply to Postgres, because there's a lot of terms out there to get confused with. So to start off with, Postgres is transactional. So what this means is that everything in Postgres revolves around the idea of a transaction. And if you're unfamiliar, a transaction is really a unit of work that's performed by a database like Postgres. And it's characterized by being compliant with something called ACID, which stands for atomic, consistent, isolated, and durable. So what does a transaction look like? If you're to think of a transaction or you're writing a simple application, the textbook kind of example is you have a series of actions you want to take. They're each their own SQL statements, and you want to make sure that if one fails, you don't leave the database in a partial state. So this example on the screen basically has one user in a bank paying another user $100. So in this case, Alice is paying Bob $100. As a bank, we want to record that this transfer actually happened, and we want to deduct from one balance and add to the another. So this happens in 3 separate SQL statements, but to make sure that if our database restarts in between one, we don't repeat one of the actions, or to make sure that we actually complete all of them, and Alice doesn't go to the bank and complain that $100 was taken out of her account, but Bob didn't receive any money, we put in a transaction, and it's Postgres' job to make sure that all of the steps complete or nothing happens at all. So in Postgres, actually everything is a transaction. And that's really important to think about. When you just log into PSQL, the REPL, and start running SQL queries that are doing write operations, they have the guarantees of a transaction as well. There's implicitly a begin and commit. This is known as auto commit in Postgres. And even when you think about selects, you have to think about them in the context of transactions, even if you're reading, because they do have the guarantees that are associated with them. So what are those guarantees? So first off, in ACID, we have atomicity. So we need to say that all transactions are atomic. What does it mean to be atomic? Basically, what it means to have an atomic transaction is that the operation is all or nothing, and there's no partial failures. This is the key reason people think about transactions in the first place. So as an example, if US Bank fails to add money into Bob's balance, it should not deduct from Alice's balance. This is pretty straightforward. It's something that we sometimes take for granted when just using these databases. Transactions also guarantee consistency. This is a big point in Postgres. It basically means that you always keep the database in a valid state, no matter what you're running. If you set some constraint in the schema, that's always going to be enforced, even if there's some failure in the database. The worst case is that your operation fails, and that's clear because it doesn't tell you, the database doesn't tell you that it succeeded, but it'll never leave the database in an invalid state. Next off, transactions guarantee isolation. Isolation is a really key term, and we're going to keep looping back into isolation as we talk about this more. The pure definition of isolation is that when you execute something concurrently, you get the same result as when you execute it serially. But basically, the point of isolation is to allow you to write queries and pretend that you're the only one writing queries against this database. It's kind of similar to in an operating system. Isolation between processes lets you act like you're the only process and you only see your memory rather than other processes. But in reality, something has to manage those processes. And there are different guarantees that you can get, like different levels of isolation in Postgres. And unless you know what level of isolation you're getting, you may have an unexpected result. So we'll talk about that soon. Transactions also guarantee durability. So durability basically means when you commit a transaction, it can't be rolled back without notice. Like when it's committed, it's committed. If there's any failure, the database restarts, etc. Your transaction has been committed. You won't be able to query this database in a state where it disappeared. Now, if your disk fails or something like that and you don't have replica, then you're in a different state. But in Postgres mind, it won't be telling you that something is not there after it's committed. So why handle concurrency altogether? So oftentimes, if you're going from like a serial workload to a concurrent workload, people think databases implement these sort of concurrency control mechanisms in order to improve performance, for example. So at first glance, people may say that if you take out concurrency control from the equation, you're going to get better. You're going to not have as good performance. But in reality, concurrency control is really a mechanism. This is obviously a little clowny graph, but concurrency control is a mechanism that is going to give you guarantees while you're having concurrency. If we just allow concurrency in the database without these kind of control mechanisms, then you're not going to get the guarantees. And sometimes these concurrency control mechanisms actually deteriorate the performance from just having anyone do anything. But then you don't have guarantees. So concurrency control's the main reason we have concurrency control is to prevent race conditions. So there are a couple of race conditions that I want to talk about before we talk about how Postgres handles them and the different features Postgres offers. So first off, the main race conditions you can think of in a transactional database is a dirty read. So basically what a dirty read is if one transaction is able to read uncommitted work of another transaction. That's really bad, of course, because the point of a transaction is to always have a series of steps and leave the database in a perfect state. So Postgres doesn't allow these, but it's a common race condition that can happen if transactions are not formatted properly. Another race condition that can happen is a non-repeatable read. This is possible in Postgres, and so are the rest of them that we'll cover here. And if you don't understand transaction isolation, you may be vulnerable to this, especially if you're running with the defaults. So a non-repeatable read is basically when one transaction queries a row, updates it based on that, maybe queries it again, gets a different result. Basically, if your reads are not repeatable, that's possible under some transaction isolation levels, which we'll go into more details. But this is one of the race conditions that your application may accept or have to handle. A phantom read is basically when a transaction sees a row that was it was first there, it makes some action upon it, and then it goes away because another transaction deleted it. This is also possible in Postgres, so we need to understand when it's possible. And lastly, serialization anomalies. These are the hardest to understand, but it basically means that when you execute things concurrently, they're not the same as when you execute them serially. And sometimes you're OK with this. It just depends on your application and what it's doing, but we'll talk about how to know if you're OK and how to prevent it if you're not OK. So if you're writing an application that has multiple threads, and you're doing concurrent actions on some shared memory, what's the classic way to prevent race conditions? Locks. You just throw some locks around all the shared memory, and you acquire a lock before you use it, so no one else can use that shared memory at the same time, and then you're not vulnerable to race conditions, right? So this is a pretty naive solution, but it's really easy to implement. It's not Postgres' main strategy of concurrency control. Some of you may say, of course, we can do a little better with locking than what I showed in the first example here, where we just lock around all access. We can have something like a read-write lock, where the readers take a shared lock, so you can read multiple times. You can read at the same time. And then the writers take an exclusive lock, so that you can't read and write at the same time, and you can't have two writers at the same time. This is also there, but we can still do better with highly optimized or high throughput concurrency. So let's look at how databases handle concurrency. So first off, it really boils down to how your database thinks. So there's really two major kind of lines of thought for concurrency control when implementing a database. There's a pessimistic concurrency control, which essentially locks everything on access with a read-write lock, where readers get a shared lock, writers get an exclusive lock, and expects that race conditions are going to happen. So it locks everything to prevent against this. It thinks of race conditions, and it thinks of conflicts as the normal case. And then there's optimistic concurrency control, which doesn't acquire locks for everything, lets you take actions, but fails to commit your actions and aborts your transaction if it finds that you're actually doing something that's going to result in a conflict or a race condition. And pessimistic concurrency control is traditionally implemented through this procedure called two-phase locking. It's pretty much the original concurrency control model for databases, dates back to like the 70s. So the original databases that were transactional were using this protocol. It boils down to readers taking a shared lock, writers taking an exclusive lock. Locks kind of build up through the transaction in the growing phase is what we call it. And then at the end of the transaction, before you commit, you start releasing those locks in reverse order, so that you don't have race conditions where multiple people are updating the same thing or depending on a certain data. Now, this isn't really optimized for high throughput, because writers are going to block readers. Readers are going to block writers, which isn't great in many applications. Now, timestamp ordering is the second class of concurrency control protocols, and it's what we call a lock-free method of handling concurrency. So basically what that means is that in timestamp ordering, there has to be some timestamp associated with every single action. And this timestamp is going to be used to evaluate or detect conflicts between two operations. And if the database determines based on this timestamp that one operation should be killed in favor of another, it will do so. The kind of policies that it uses to do this is definitely implementation specific. So we're going to get into how Postgres implements timestamp ordering through like a little sub-protocol, if that makes sense. But the key thing about any timestamp ordering protocol is that you have to make sure that the timestamp is monotonically increasing. And what this means is it never goes backwards, it always goes up. If at any point the timestamp that you're using, which can be a number, it can be a real timestamp, it can be whatever, goes backwards, you're going to have problems, and your guarantees aren't going to hold up in your concurrency control strategy. And we'll talk about how Postgres ensures this. So how does Postgres handle concurrency? Postgres implements something called MVCC. Does anyone know what MVCC stands for? OK. Multi-version concurrency control. So that's a mouthful to say, so we mostly just say MVCC for the rest of this talk. But basically what it means is that in order to handle concurrency, Postgres will make multiple versions, aka snapshots, of your data for every write transaction. And this works in a way that reading never blocks writing, and writing never blocks reading. This is kind of the golden rule that everyone will tell you if you're using MVCC. Don't worry, your readers won't block your writers, and vice versa. It's kind of why MVCC is popular today, and like the most popular concurrency control mechanism in the last decade for sure. So now we'll talk about how this actually works, because it sounds a little magical at first when you're coming from a 2PL or two-phase locking background. So let's imagine at time equals 0, so at epoch, we insert a record. and we just inserted one record into a table. It's a tuple with 2 values. Basically, in your mind, we just have one row in the database. And what MVCC does is it stores one row with some additional context per version. So initially, this additional context is a tuple. It's a begin timestamp and an end timestamp. The begin timestamp is basically when was this row inserted, or what was the number that's associated with this insert operation. And the end timestamp is when is this row expired, when is it not relevant anymore. So initially, this is going to be something to represent the value of infinity, the end timestamp, because you've inserted one row. It's not expired by any means. You haven't updated it. You haven't deleted it, etc. And the begin timestamp is going to be when you started. In this case, we started at t equals 0, so it's 0 here. So now imagine at t equals 2, we actually go and update this record. And say there's a user Bob in a game, and we set his score to 5 from 2. So what we see is that MVCC adds another row into the internal representation of the data store, where basically we have the begin timestamp of this row, an end timestamp of this row, and a pointer to this actual data. And what happens is the end timestamp of the first row is atomically changed from infinity to 2, because that's when the next transaction started at timestamp equals 2. And the end timestamp of the new row is infinity. So now imagine that at t equals 3, we go into the database and we try to read the row. So what happens when we read it? We have one row which is valid from 0 to 2, and one row that's valid from 2 to infinity. So if we select at t equals 3, the first row is not going to be valid because our timestamp that we're using, our snapshot for this transaction, is greater than the end timestamp of the first row. So we're not going to read that one. Instead, we'll be reading the next one because it hasn't expired yet, and it began before our transaction, so it's visible to us. So at t equals 3, if we issue a select, we will see the second row, which is really the update. So now what happens when, so we'll see the second row because it was updated. So now imagine at t equals 4, we try to delete the row that we've inserted and now updated. Basically, what happens when we delete is the data doesn't actually go away. Instead, the end timestamp of the second row, which was previously infinity, is changed from infinity to 4, because at t equals 4, we issued the delete. If we read again now at t equals 5, neither of the rows are valid, because 5 is greater than the end timestamp of both of them, so we can't see anything back from the database. But if there's an old transaction sitting open, and it was running a statement that was blocked for whatever reason, at t equals 1 is when it started, then we'll actually still see the first row. And this is kind of how Postgres allows for high concurrency. Basically, every transaction or every statement, depending on your isolation level, which we'll get into, gets this snapshot level associated with it. And that's a number. And if that number is within the bounds of a different row version, then it gets to see that. But if it's not, it doesn't get to see it. So this allows us to not just have an entire lock over the database whenever we're doing a write operation. So how does Postgres actually model the version chain internally? So what we just saw is how MVCC is implemented at a high level, but let's look into how Postgres actually implements it. So instead of seeing begin and end timestamp for every row, for every version of every row, you basically have an xmin and an xmax in Postgres. And x stands for transaction, to kind of drop the t there, and really it's a transaction ID. So so xmin really stands for the lower bound of the transaction IDs that are allowed to see this row, and xmax stands for the upper bound of transaction IDs that are allowed to see this row. And instead of a timestamp, the transaction ID is a monotonically increasing number. Internally, it's not exactly a sequence like you would get when you run create sequence, but effectively, it is the same. It's a 32-bit number. So in integer, just to clarify. And it always gets incremented and goes up. So let's take a look under the hood. So in this example, I create a simple table with one field in it, I, which is an integer. I insert some arbitrary row into it, and I select it out. And when in my select statement, you'll see that I select for xmin, xmax, and then all the columns that are available in the schema to the asterisks. And what we get back is actually xmin and xmax. So these are kind of hidden fields that Postgres is keeping with your row version, but it only shows you the latest version. So first I do a select after the insert. I see that the xmin is 557. The xmax is 0. So 0 here is basically Postgres' representation of infinity, and we'll talk about why shortly. But then after I run an update on this row through Postgres, just through the REPL, and I actually ran this and just copy-pasted it, and I set the value to 2 instead of 1, which was initially inserted, and I select again, I see that the xmin's gone to 558. So basically 558 was the transaction ID at that update. And this row is also not expired. Its xmax equals 0. We'll talk about that now. So basically, every transaction row, every version row has an xmax, which is initially set to 0. And then if a transaction wants to expire that xmax, it uses a protocol like compare and swap. So you may be familiar with the processor instruction compare and swap. Basically, you want to change a value, a variable, to a new value. But when you're changing it, you want to make sure you do it in a way that you're not changing something you didn't expect. So you tell this function, I want to change the value from 2 to 3. And if it looks and the value is 3 already, and the value is 4, it won't change it back to 3. It'll only change it to 3 if the value is 2, if you ask it to compare and swap 2 to 3. So Postgres really, when you're trying to expire a certain version, each transaction issues a compare and swap from 0 to the expiry time, so that if another transaction tries to expire something before another transaction, one of the compare and swaps will fail because the value has been changed in the meantime. So this is how Postgres kind of handles race conditions on the expiry part, which is especially important if you have multiple cores available for your database. So CAS is also used to implement like user space mutexes and tons of things in the operating system. So this is pretty much an overview on how MVCC works, but we didn't cover one really important part, which is vacuums. So who here has heard of vacuums in the context of Postgres? OK, great. So a lot of people have, it seems like roughly 50%, a lot of people have heard of vacuums. Not everyone knows exactly what they should do. Most people who've been administering Postgres should know that they need to run them regularly, though. Like a Dyson, a vacuum is very powerful, has many options. And we need to know what the difference between them are to use them effectively, unless we go with Postgres defaults, which we'll talk about soon. So what happens if we just take out vacuums from the equation of our Postgres server, which is in production? Well, if you look online, there's a feature called auto vacuum, and you'll see some people recommend to even turn it off or tweak it or something like that in Stack Overflow posts. Let's hear what would be bad or why it would be bad if you remove vacuums altogether. So really, there are two possibilities when you remove vacuums. You're going to run out of disk space, or you're going to run into really weird stuff after you run a number of queries. And we'll explain both of those now. So first off, in MVCC, we showed that when you delete, when you update, et cetera, all you're doing is inserting more and more rows into this version chain that's assembled by Postgres behind the scenes. So what happens to those old versions? Like, if there are a ton of open transactions and we need to know if anyone's using it before we clear a row, this process is not happening each time you commit a transaction. It basically happens in a routine batch process called vacuums. And at a high level, the process of a vacuum is rather simple, but it's necessitated by MVCC. Uses the concurrency control mechanism. So basically what a vacuum does is it goes and looks, OK, what's the lowest open transaction ID in your database? Look at the lowest XID. Now, delete all the versions where that lowest XID is above the Xmax of those version rows, because all those versions are not visible to the oldest transaction in your database, so they're no longer relevant. The vacuum sweeps them up, just reclaims a ton of disk space, and if you don't vacuum, if you take it out of the equation, then you're basically going to keep everything. If you keep everything, you're probably going to run out of disk space. But something else can actually happen if you keep everything. And this isn't quite as expected. So basically, theoretically, how many transactions, does anyone know roughly how many transactions we can have open at a given time? It's just a trivia question. More or less, yeah. So XID is an innate, right? we need the -1 there. But yes, we can have 2 to the 32 minus 1. Transactions open at time. This is theoretically, of course, most likely you'll run out of memory if you try to do this because work mem, there's other constraints. Theoretically, this is the limit, but it does kind of matter. What happens when you keep one transaction around, like say xid equals 2, and this transaction is never closing. It's up for days, maybe months. And though 4 million transaction IDs sounds pretty high when you have an incrementing number, let's say it's open for months, just sitting there as an idle connection. You have no sorts of timeouts in your system. Eventually, if we hit transaction ID 4 million, because we need to keep incrementing the number, we'll have to wrap around at 0. And then we'll get transaction ID 0 again. But if you have transaction ID, say 2 or 12 or any number less than 4 trillion, open still, the vacuum won't be able to clear the rows older. So A, you're going to have a lot of disk space. If you don't run out of disk space in time, you're going to have really weird situations when you have transaction IDs that are not monotonically increasing because they wrap around at 0 and you have things above 0 already. So if your XIDs wrap around, you're in a soup. I've seen numerous postmortems online. You can look them up for pretty big companies, and not their fault, like Sentry, Joyent, that have just had outages due to transaction IDs wrapping around. So basically, at a certain point, Postgres will start to try to kick in vacuums. At that point, you need to pretty much, you have 2 choices. You accept data loss because something's weird is going to happen when you wrap around your transaction IDs, since the whole idea of concurrency is lost. The whole idea of MVCC's guarantees is lost, since it relies on monotonically increasing numbers. Or you have to stop the world, kill all your open transactions, let the vacuum finish, and get back up. And that's basically what happened in both of these cases in Sentry and Joyent. And the postmortems are online. So if you don't have like another cluster to fail over to or something like that, you're pretty much in a soup and you have to take a step back, accept outage or data loss. I've actually seen this error message, but luckily it's in staging. Basically, if you open up pSQL at this time when you have really high XIDs and run any query, you will get warnings over and over saying that your XID is going too high. If it goes higher, you're going to hit wraparounds. We're trying to run vacuums. It's blocked on other things. Please call your transactions. Not in those words, of course, but we'll see something to that message. And at that point, you need to take action. If you run a Postgres server, there's another talk on monitoring, but this is very important to monitor. Because if your vacuums are not running in a timely fashion, you're definitely going to run into a problem because of it. So Postgres 9 has a feature called auto vacuum. You should use it if you can. If you don't know about, or if you've been running Postgres for a long time and you haven't been worrying about vacuums, you're likely using it because it's on by default. Basically, it uses table statistics that are periodically updated to know when it has a certain number of dead rows and when it should start cleaning up. This works well for most all use cases, but if you refer to the docs, there's a number of flags that we can tweak on it to do different things, have different aggressiveness, etc., which is really dependent on your workload. For example, if you have like an update-heavy workload, depending on how slow you're OK with things being, you may not want to run vacuums aggressively, or maybe you want to run them in the night or something like that when you don't have users up. So just like a house, if you don't vacuum routinely, things will pile up. Garbage will pile up in this case, and you're going to regret it. But just as powerful as normal Dyson vacuums, we have the auto vacuum in Postgres 9, and you should really use it if you can. So we've talked a lot about MVCC and how it allows for highly concurrent workloads, which is one of like the huge advantages of Postgres when you're talking about concurrency. But it comes with a lot of complexity, for sure, because it's a lot harder to reason about mentally than, say, the two-phase locking approach, where you just acquire locks, everyone else waits, you release the locks, everyone else proceeds. So the performance gain is worth it, but in databases, we care about performance and guarantees. So let's talk about what kind of concurrency control guarantees we get with MVCC, what more we have to think about, and what's still upheld. So the golden question that everyone asks if they're managing a database or writing an application that has a heavy concurrent workload is, how do I prevent race conditions? Most people think, or many users of databases, especially people who are new to them, think that if you use transactions, you solve race conditions. You want to do something in a isolated view of the database, open a transaction, run some queries, no one interferes, right? Well, with MVCC, this isn't really always the case. with a lock-free concurrency control mechanism? It really depends. Out of the box, things may not really work as you expect. If you think that all race conditions are solved by transactions, even at the database level, not at the application level, then you may have some race conditions right now in production. So it really depends on your transaction isolation level, which is something that we mentioned a few times earlier. And now we're going to go into what it really means. So yeah, if you're unfamiliar with this term, you're probably subject to race conditions already due to the defaults. And these race conditions may or not matter in your apps. In many apps, they don't matter. The defaults are pretty sane. So in SQL, just like in the ANSI SQL spec, we have 4 levels of transaction isolation. There's read uncommitted, there's read committed, there's repeatable read, and serializable. We'll go into each of these. But to start off, Postgres does not allow read uncommitted. Basically, read uncommitted allows for dirty reads. It just means you read everything. If you're using that, you probably shouldn't have transactions in the beginning. Postgres does not allow this. But by ANSI SQL specification, I thought I may cover it just to clarify that there's no chance of dirty reads in Postgres. So what does read committed, the lowest and default isolation level in Postgres, really guarantee us? So basically what read committed means is when you open a transaction, each very statement of the transaction, so if you have 3 statements, they each get a certain snapshot of the database. They each get to see a certain snapshot of the database. And that snapshot that they see is based on the start time of those statements. So you don't have like one XID for the whole transaction. If you're using read committed, every statement gets to see the most recently committed data. So this allows for like a variety of race conditions and anomalies when you're using data, especially in a highly concurrent application, right? So since every single statement in your transaction gets to see the latest view of your database, you can have non-repeatable reads, which means one transaction may produce a result. One statement in your transaction may produce a result based on data that was no longer there in the third statement. And that may or may not be a problem, again, for your application. We'll talk about some ways it could be problems. Another problem is phantom reads. You can be reading data in one statement in your transaction. It could be deleted later in the transaction. And the last way is just serialization anomalies, and this one's pretty tricky to understand, so we'll go over it in its own whole slide. So the next level of transaction isolation in Postgres is called repeatable reads. And basically what repeatable reads does is it extends upon read committed, and it says, okay, this is how most people think about transactions if they haven't actually looked too much into Postgres. Basically, when you open a transaction, you get a certain state of the database, you get a certain snapshot, which correlates to a certain minimum transaction ID, and all statements in the transaction see data after that point, see data from that point in before. And this still allows for one type of anomaly, which is more complicated and really depends on your application, but it removes the possibility of things like phantom reads or non-repeatable reads, like we discussed in read committed. So with repeatable reads, you can read the same thing twice and you'll get the same result, but there still is an anomaly. So basically, imagine we have this scenario, and this is a textbook example in Postgres docs, in a second quadrant blog post, if I recall, and many other places. But imagine we have a bank that needs to verify that the sum of all your account's balances is over 0. So basically, we have, and now imagine that we have 2 transactions that run in parallel. So if we just needed to verify that one account balance is over 0, we can set a constraint in the database. And we can say this value needs to be greater than 0. But when we have 2, it's not that simple. So we have to make sure that our application is not vulnerable to race conditions, especially for something like a bank. So basically here, transaction 1 reads both accounts' values and says, OK, it's going to be above 0 if I remove 100 from account 1. And then transaction 2 may read both accounts' values and say, OK, it's going to be above 0 if I remove from account 2. Now, since transaction 1 and 2 are updating 2 completely separate rows, there's no conflict when Postgres looks at it. It says one transaction is reading 2 rows, updating one of them. Another transaction is reading 2 rows, updating the other one. Those writes don't conflict with each other because they're completely separate rows. But in your application, you actually have a guarantee that you need to uphold, which is that the sum of all account balances is over 0. So Postgres will update both rows, and you can end up in a state where the sum of both balances is 0, because it's not enforced by a constraint or anything like that. So there are a variety of ways to handle this case. You can solve it by explicit locking, right? You can lock the row, but if you're going to lock the row by yourself, you're not really getting the benefit of the database's concurrency control mechanisms, because it's supposed to provide like a good abstraction, right? You can also like enforce in your application. You just make sure that you don't update both account balances at one time. Maybe you do this outside Postgres, maybe inside Postgres, with some sort of write dependency. But the easiest way by far is to enable the serializable transaction isolation level, which is the highest level available in Postgres and the SQL spec, actually. And it's one above repeatable reads. Basically, the transaction isolation level of serializable is deterministic. When you execute transactions serially and concurrently, you're guaranteed to get the same result. It never sacrifices anomalies or isolations for the chance of some sort of anomaly that we talked about earlier, like serialization anomalies, like in the example of this bank. But it does come with a downside, and that's why it's not the default. Basically, what happens is when you turn on the serializable isolation level, Postgres will start looking at the pattern of your queries in the transaction. So one transaction reads 2 rows and then writes to a row. Another transaction reads 2 rows and writes to a different row. It's going to know those two read 2 rows before they wrote. If the state of that one of those rows that read changed in transaction 1, and transaction 2 is looking at those rows before writing, then maybe there's a write dependency there. Maybe what it read affects what it writes. So if 2 things do that, Postgres will have to abort one of them. So this means that sometimes you may have transactions aborted even when it doesn't matter in your application. Like maybe you don't really care about that race condition in your application, but because you're in the serializable isolation level, you're going to have them aborted just because Postgres thinks there may be a dependency. After all, it doesn't know all the rules in your database. This isn't very declarative, if that makes sense. But if you have a problem like this, you're probably better off going with serializable isolation level and just retrying when there are aborts, rather than risking anomalies, because it's much harder to track it the other way. So the reason it's not default, just to clarify, is because of these frequent serialization failures whenever you have a dependency violated. And another thing you really have to make sure whenever you use serializable isolation level is because of these frequent aborts, you should never consider your data good until it's committed. Now, you should really never do this anytime, but if we're using serializable, it's a common case. It's not an edge case. It's not like upon failure, your transaction will be aborted. It's like your transaction can be aborted during normal concurrency. So without understanding transaction isolation, you can fly by 95% of the time. Like, you mostly won't have any issues, but that 1% of the time that you do have a race condition, it's going to be very confusing, just like this argument. Imagine there are 2 developers. One is saying that this is possible, one's not. It's very hard to say because it's not deterministic. So if you have to think twice about what transaction isolation level to use, or if you have to think twice about whether serializable anomalies matter in my case, and you're dealing with something very crucial, like a bank, for example, use serializable and just be safe. This is actually a reason that a lot of banks just use 2PL, or two-phase locking. But serializable is obviously a little better than two-phase locking because you don't lock all the time. So you can get a higher concurrency throughput here. But you do have that downside. Oh, sorry. So in summary of transaction isolation levels, this is a quick chart to help you understand what isolation levels have what issues. So read committed the lowest level. It's 3 levels of isolation errors. This is usually fine, but just don't assume that transactions are the magical solution to all race conditions. It's a very common beginner mistake. Repeatable reads gets rid of like almost all race conditions that most applications have. But if you're having really serious ones, which are write dependencies that you can't express to the database, then use serializable. So MVCC and isolation are the most important parts of concurrency in Postgres by far. If you don't understand those 2, you're vulnerable to many, many issues in the long run. But there are some other things in Postgres that are good to understand if you're administering Postgres, especially in a database which has high concurrency and high throughput as you're scaling Postgres. So we'll discuss those at a little high level. So first off, we've been acting like Postgres doesn't have locks this whole time. Though MVCC itself is a lock-free concurrency control protocol, there are locks in Postgres. They're light locks that are taken for various operations under the hood. But Postgres basically hides its locks. It doesn't make them like the forefront of your concurrency control, like a TPL mechanism. But they're still important to understand if you face some very odd issues. So you don't need to be an expert in the taxonomy of locks. Basically, different locks have different levels. Different operations take different locks. This is something that you can pretty much view documentation for pretty regularly if you face any issue that seems like something's waiting too long on another thing. But you should know where to look. So there's basically 2 places to look if you're running into a case like this. First off is PG stat activity. It's a system table that's in Postgres. Just comes with it. You query it. You can see all the running queries, and one of the fields is waiting. That'll be a Boolean. If your query is waiting on some sort of lock dependency, it will be true there. If not, it'll be false. So that's the first thing to see. Is my issue related to locks, or are things just slow? If your issue is related to locks, start digging into PG locks, which is like your best friend that's on call. You just need them sometimes. They're very easy to reach. It's just a system view that comes with Postgres. And it can express the lock dependencies between all locks in your system. But it's a little cumbersome to query. There's great queries you can copy and paste in the wiki for this, for very common operations. So one thing that you need to keep in mind when you're dealing with locking in general is the presence of something called a deadlock. So whenever you have locking, you have the possibility of deadlock. That's inevitable. The question is, like, how do you tackle that deadlock? And how do you make sure it doesn't stop the world, right? So what is a deadlock? So imagine we have transaction 1, transaction 2. Transaction 1 wants to update object 1, then object 2. Transaction 2 wants to update object 2, then object 1. So first transaction 1 updates object 1. Next transaction 2 updates object 2. And then they try to update the ones that the other one just updated. So at this point, they're both waiting on each other. Transaction 2 is waiting on transaction 1's lock to release, and vice versa. So without any deadlock protection, we're going to wait forever. Since Postgres is an optimistic concurrency control protocol, and it assumes this is not the normal case. And resolving deadlocks is slower. Is the slower path. It's not the faster path like in a 2PL mechanism where you just don't have deadlocks, but you make everything else slow. So how it works is Postgres really makes after a statement waits on a lock for over a second, and that time period is configurable, Postgres will generate a graph of lock dependencies between each other. And if it finds a cycle, it will say, OK, there's a deadlock here. I'll kill one of them, and the other will proceed. And then you retry your transaction or something like that in your application. But it waits for a second before doing this because there's a performance penalty for just doing it all the time. So Postgres assumes that since deadlocks are not the normal case, we'll prioritize your normal application case and then just check for deadlocks after. So that's why there's the 1 second delay. A pessimistic concurrency control protocol would just make sure deadlocks don't happen, but impact the performance of everything regardless of your application has deadlocks or not. So another trick that you can use, which isn't related to deadlocks or locks in general, but well, it could be, depending on your operation. But it's basically this onConflict keyword that was introduced in Postgres 9, I believe. So if you use Postgres 8, then you can't use this one. But basically, it means that when you do an insert operation, you can say onConflict a variety of operations. You can do nothing. You can update the value that's inside the database, et cetera. You can use this to emulate upsert operations, but another good use case for it is just not having aborted transactions due to maybe some sort of at least once delivery in your pipeline. So imagine you have a queue that has at least once guarantees. You read a message from the queue. You make a Postgres query. If that ID appears once and you're trying to insert it, then at least you won't have to handle errors like aborted transaction, or sorry, like you won't have to handle conflict errors, something like that, which is harder to decipher. But in this case, Postgres will just succeed because the value is already there if you use do nothing. So this is pretty useful when you have at least once deliveries, but it's also useful for upserts. Yeah, and it's really useful for batch operations because say you have, since every operation in Postgres or any transactional database needs to be atomic, like it either fully succeeds or fully fails, If you're inserting like, I don't know, 1,000 records at once, you don't want to have to retry 900 of the records and decipher which one had a conflict just because one of them has a conflict. You want to just be able to tell Postgres, OK, if one of them has a conflict and I don't care about inserting that one, ignore it. It's a lot easier. So that's all for this talk. Thank you very much. We do have 5 minutes, so I'll be open for questions. If you're interested in talking more about Postgres concurrency or anything for that matter, come talk to me afterwards. I also work at a startup called Segment, which is a data infrastructure company. And if you're interested in that, also reach out. Any questions?
So what's the default transaction isolation level?
It's a read committed. So it's the lowest transaction isolation level that Postgres offers. Again, it does have like a variety of anomalies that you can face. It's important to understand these anomalies. Most applications won't be vulnerable to them just due to their workload. But if you are vulnerable to them and you start seeing the effects of them without understanding the cause, just trust me, they're really hard to decipher what's going on. So, any other questions? Oh, actually, could you go up and ask the question there? Sorry. Forgot to ask that before. And it's recorded.
So I'm an RDS user.
Mm-hmm. So am I.
In my little monitoring, my transaction IDs are going up and up and up and up. When do those reset? And I guess I need to be concerned about it by the time it hits around 2 billion.
So 4 trillion is like the limit here. But you should be concerned if they're going up in general and they're not ever flushing back to 0.
Yeah.
Or a low number. You may not see them exactly at 0.
0.
Sorry.
It's the age, right? So you're always going to have something.
You're always going to have something, yeah. Not 0.
Yeah.
But if they're continuously going up, that is worrisome over a long period of time. That means that you probably have something, either you have something running that's just not being killed, or like some open transaction that's just running for a long time, and you should look in pgstat activity to see if you have that, or you have you're just not vacuuming at all, like vacuum's off or something.
Basically, if they exceed the value of auto vacuum freeze max age by a significant margin, that's one of your configuration parameters. That's the point that Postgres will fire up an auto vacuum process and re-vacuum a table. So if you see, by default it's I believe 200 million. So if it, but check for your system how it's configured. If it exceeds that for it to just like pop up a little bit above that is normal because just auto vacuum hasn't finished yet. But if, for example, it's 200 million and you see it at 220 million, that's something to be concerned about.
Yeah,
I'm at 6 million.
Yeah.
I thought you said 2 billion. Sorry.
Go back to
6 million is good. Sorry.
Okay.
Thought you said 2 billion.
What you'd expect to see on that sort of curve of our graph is, I work on RDS, is that you expect to see basically that curve to go up to 250 and above it, and then auto vacuum to kick in if you haven't done anything else. And then it'll come back down, and then it'll go back up, and so it just looks like this sort of wavy line. But you have to hit enough to have a problem, right?
Yeah. If you have low throughput in general, you may not hit this for a very, very long time. Especially if you just loaded a bunch of data in Postgres and are just reading. You're not going to hit this threshold for a long time. But do be concerned if you do hit the threshold and go above it for a very long time, and the vacuum is just running and it's waiting. Because even if it fires up auto vacuum and you're doing something like dropping an index and it's blocked on something else, you can run into situations where you need to make sure you kill those other transactions that are blocking the process. Otherwise, you'll hit wraparound and other issues.
Cool, thanks.
OK, we're all out of time here. But feel free to ask me for any questions afterwards.